Okay, so in this video we are going to talk about the case where that we are having zero initial displacement. So before we were talking about zero initial velocity. Now we are going to talk about zero initial displacement. Okay, so simply we are going to solve, this is the derivation, how we are going to derive it, okay? So we are going to solve for initial boundary value problem, very simple and easy mathematically, for the displacement of the string if there is an initial velocity but no initial displacement. So we have some initial velocity and the initial displacement is going to be 0 in our case. So the problem, after making some derivation, okay, after making many derivations, okay, like they are simple actually, not difficult, you are going to end up with this equation. So this is what really we are interested in. This is the wave function again, yx of t, yx and t, 2 over pi c. This is, as we said, the constant related to the density of the rope or whatever, something like characteristics, fixed characteristics of the wave itself. It's going to be given or known for us, and we are going to have summation of some terms from n equal to 1 to infinity, 1 over n, number of the terms that we're going to have. We're going to have here, the first term is related to an integration from 0 to L, g of z sine n pi z over L, times another term that is giving us the contribution of x, right? N pi x over L, times another term which is going to be sine n pi c t, contribution of t over L. Okay, and always we have c here and c here, which is the constant. What is the difference between the previous one, which is zero initial velocity? Yes, seems here cosine, for example, it was cosine here. Also, this part for the coefficient was different than before. Okay, so that's it, and we are going to give an example on it, and you're going to find that it is very easy to apply it. Okay. Now, suppose the string is released from its horizontal position, okay, with an initial velocity given by g of x equal to this value. Okay, so this is actually for the same what we have already explained before. So our case is going to be for a function that is going to have initial velocity given by this function. Okay, as I said before, why the initial velocity is not going to be given as one value? Because we have like wave, so we need to think about this as a wave and think that at every point x there is value for y. So we are going to give it as g of x equal to x times 1 plus cosine pi x over L. Okay, our equation, which is 16.6, this is our equation here. This is our wave equation, is going to be used in this case. Okay, so first compute the integral. This is the most important part, which is this part. This is the integral that we want to start with. This is the most important part, or the difficult part. The other parts are going to be easy to be obtained. Okay, so the integral is going to be from 0 to L. Remember that we are in like interval. Okay, we're talking about intervals. G of z sine n pi z over L dz equals to 0 to L. This is the function that we have, okay, which is x, here it is z, 1 plus cosine pi z over L, cosine pi z over L, and then multiplied by sine n pi z over L, n pi z over L. Again, it is exactly what we are having here, sine n pi z over L, and then this is our integration parameter or integration variable, right? So we are dealing with our case. Now we are going to have two cases here. For n equal to 1, we're going to find this integration is going to end up with 3L squared over 4 pi, and for other values of n, which is from 2, 3, 4, and whatever, is going to end up with this fraction. All of it function of n, pi, and n and L, and raised here to the power n. Okay, so the solution for this is going to be the solution for this coefficient here, it is going to be something like this: 2 over pi c 3l squared over 4 pi, this is our case, sine pi x over L sine pi ct over L. Okay, so we're going to end up with this part. Okay, plus 2 over pi c, the summation of from n equal to 2 to infinity, this fraction here we have obtained, okay, because we are dealing with an interval, okay, because we have one interval n equal to 1 and another interval n equal to 2, 3, 4 and so on. So this is going to start from n, however that this is the first term, it is going to be dedicated for n equal to 1. This is why you cannot see any n here. However, here this is the second part of the interval, or the second part of n, I mean, which is going to be starting from n to infinity. This fraction, function of n, sine n pi x here over L, sine n pi ct over L here. Okay, so we are ending up with these two parts, like superposition of two terms here. With c equal to 1 and L equal to pi, these are special conditions for us. As I said, the limitation of the interval is always given for us, and this c it depends on some characteristics that we should know it. So this solution is going to end up with yx of t, which is the wave function that we are dealing or searching for, equals to 3 over 2 sine x sine t, sine x sine t, plus the summation from n equal to 2 to infinity, this term, this nice term, times sine nx times sine nt, because we have here c equal to 1 and L equal to pi, so already they cancelled out, and then we are ending up with nt. Then we need to know how this wave function is going to be represented, okay, graphically. So let's go here. Yes, we can find it like this. So we're going to find that this is the function. First of all, this is the interval from 0 to pi, okay, from 0 to pi, 3.14 something, and then we're going to end up like this is the starting of the first wave. As I said, it is starting with initial velocity, okay, initial. Here we are talking about zero initial displacement, and we are having some initial velocity. So this means that, for example, here we are like making something for the rope in the beginning, velocity for it, so that we're going to find that the initial starting of it is going to be something here, for example, and then you are going to find like it goes at 0.2 with this shape, 0.5, 0.7, 1.3, 3.4, and then it proceeds like this. We call it wave moving downward for increasing times, okay. This is as we said in describing the wave from 0.2, 0.5, 0.7 and so on. Okay, so I hope that we can understand it easily, because really it is very easy to apply the zero initial displacement. Thank you, and see you in the next video.